Hello, my name is Anshuman Dhuliya and I am presenting our work on synergistic program analysis. So, synergistic program analysis, what it does is it enables interaction between analyses in a very flexible manner, we will see. And I will talk about the need of interaction first. Why do we actually need interaction, modeling the issues in interaction, and then introduce synergistic program analysis and its application to demand-driven methods. So if you look at this program, we know that at line 3, b is equal to star u. B is basically 10 because u is pointing to a and a is 10. So if we run constant propagation on this, we get b is not a constant. And this is basically because constant propagation cannot find out what star u is. It needs points to analysis, which can actually basically provide the information of what star u points to. And here it can, constant propagation can correct that b is actually 10. So we are trying to automate this interaction. So existing techniques involve automatic based on valid transformations and abstract transition systems. And there are manual methods of redesigning data flow equations over the product lattices, which is very effort intensive and which we are trying to avoid, and we want the method to be automatic. So modeling the issues in interactions. So if analyses don't interact on the same statement, they all go their own way. Doesn't matter which direction they are in. So this is a backward analysis AB. So there is no interaction between them here. So if we model the ideal interaction, the product, so what happens is for the same statement, for a single statement, each analysis interacts regardless of whether it is backward or it is forward. So for example, in this case, points to analysis would be interested in what B is because it could eliminate one point T out of A and B, and some value analysis might be interested in what star U actually points to. So a forward-backward example of interaction is a Liveness based points to analysis, where Liveness goes backward, points to goes forward, and they are interacting on statements. So one way to achieve this is cascading, and cascading, what it does is, for example, this is the program. So it will run points to analysis first and transform star u to A. Then it will run CP analysis on it and transform B to 10. So what happens is points to analysis runs first, evaluates star u, and then CP analysis runs. So CP is basically using the information from points 2. However, the information delivery is not very sound, basically because star u might point to more than one point T, and that cannot be transformed into the program. It is not a valid transformation of the program. So and secondly, the issue is if CP runs first, it has no points to analysis before it to actually utilize the transformation of. So you have to run CP after points to analysis, and this is known as a phase ordering problem. So if you compare the ideal method with cascading, what happens is cascading gives an order to things. So there is a phase ordering. So only analysis coming afterwards can use the information from the analysis before, and if the red analysis has to communicate with has to use the information from the blue analysis, red has to come after the blue. So there are instances where they are carefully iterated in a well-defined sequence in many of the compilers, but no sequence is the best. Ideal solution should be like every analysis should interact in the same phase. So in respect to other contemporary approaches, the ideal method enables very effective form of communication. However, the method of communication used in automatic approaches is limiting, therefore it is represented like with dots. And if there is a backward analysis, again you have an ordering. So let's look at the span framework. So the issues, and we'll look at the issues and the solutions in the span framework. So removing constraints of valid transformations. So let's take this example, temp is equal to star x. So x points to either y or z. So no transformation engine can actually transform this to temp is equal to x or temp is equal to y. So actually the program transformation is out of the picture. So whatever you want to do is you don't want to transform the program. So effectively, what you want to do is temp points to y and z, and effectively it translates to, in some executions of the program temp is y, and other executions of the program temp is z. Temp is equals z. You need to analyze them separately and combine the result and then transfer the result to the next node. So that is how span works. It simplifies the statement star temp is equal to star x to this and computes the final solution. So constraint of valid transformation. So what happens is, due to the transformation, this information couldn't have been communicated. However, span, which doesn't use transformation, is able to communicate more effective information to other analyses in the same phase. So the other aspect is automatic selection of analysis. So with respect to other analyses, other approaches for analysis to interact, what span does is, span doesn't need the user to specify which analysis does it want the system to put together. So span uses the expressions present in the program to actually do this. So for example, some analysis may find some expressions difficult to analyze. So star x, most value analysis cannot do except only the pointer analysis. A greater than b, relational analysis are good at evaluating these expressions, not constant propagation, etc. And the conditions, what b is actually, so true or false. So how can you evaluate it? Many analysis cannot. So there are some very useful simplifications of IR expressions, star x to set of variables, a greater than b to a boolean value, if b to, by eliminating true or false branches. Some analysis may have information to simplify a particular expression. So for example, star x can be simplified by a points to analysis. A greater than b can be simplified using range relation analysis. If b can be simplified by constant propagation parity analysis, and this can be useful to many analyses. So one of the issues most frameworks can't handle is making forward compatible with the backward. So forward analysis cannot communicate with the backward analysis, and you have to introduce a phase. So span can enable interaction between backward and forward analysis. And if we compare it to the ideal solution, so if you have a backward analysis in the mix, you can run it along with the forward analysis in the same phase without introducing a new phase. So with respect to learners, if you have at least even one backward analysis, you will have to introduce phases. So for example, constant propagation and strong liveness both can interact in this case, in this particular program. So the false edge is removed because of the help of constant propagation, and strong liveness can know that x is not live, okay, above 4. Constant propagation can eliminate some redundant data flow information because it knows x and b are not live ahead, and strong liveness can give it that information. So this is how constant propagation and strong liveness communicate. So combining similar data flow information. Now when we are combining multiple analyses, what happens is, multiple analysis can simplify the same expression by giving a similar data flow information. For example, x is equal to star u. One points to analysis gives x, u points to a, b, c. Other points to analysis gives the information u points to a or d. So what happens, span combines those results. So first using the simplification by points to 1 and simplifying it to x is either equal to a, b or c. Then uses the information from points to 2 to eliminate the spurious information. Because points to and points to both analyses are sound, so their intersection would result in a sound pointies. Now enhancing the demand driven method. So let's see how strong liveness communicates with constant propagation. So suppose this is the program, and strong liveness What it does, it starts from 3. Why? Because 4 and 5 are control dependent on 3, and since 6 and 7 are reachable only after 4 and 5 are reachable, they are all marked unreachable. Now liveness analysis starts from node 3. So as soon as it starts from node 3, it gets to know that this is a conditional statement. So if someone can give me the simplification of this conditional statement, I could further go and analyze 4, 5, 6, 7. So the system marks this demand and lets the strong liveness go ahead with its liveness information, and since B is dead over here, the liveness information is stopped at 1 and 2 in. Now as soon as liveness information reaches a fixed point in the small 1, 2, 3 nodes, what constant propagation does, it starts from 1 and reaches 3 with the value of B as 1. Fine. So note that X is also coming, although it is not live yet, because, and this arrow indicates that constant liveness is using constant propagation is not using liveness as of now. These things are very configurable in the system, and to make this example a bit simple, I made these assumptions. So now constant propagation comes in and finds that B is 1 at 3. So it, using this information, the system marks the true edge as feasible and false remains at infeasible. Now constant propagation after 5, 6 and 7 are marked as feasible. It analyzes it and reaches a fixed point because there are no loops here. And liveness analysis then analyzes 7, 6, 5 and propagates the information back. Now if strong liveness, if we were only interested in the results of strong liveness, constant propagation did redundant computations at 5, 6 and 7 and also made redundant computations regarding X because we only needed the value of B. Okay, so here what actually happens is we need to raise the demand of constant propagation, and that needs to go further, and only that demand needs to be met. So what we did, we augmented demand driven method with spans interactive ability. Thus raising demands led to interaction between many analyses. We added 76 assertions to the spans test benchmarks, and out of that 51 assertions passed using the span enabled demand driven method. 16 assertions were already passing without using that spans enabled demand driven method, and this gave us about a 3x improvement. The timing of the whole computation basically depends on the number of analyses that are interacting. So the analysis we used were interval analysis, points to analysis, even odd and parity analysis. And relatively on an average span enabled demand driven method, it took nearly 2.3x more time than the normal demand driven method. So, and we can improve on this. So we can basically improve on this on using simplifications, faster simplifications. Thank you. These are the references.